Hello friends, today's question. A ball of density d is dropped on a horizontal solid surface. It bounces elastically from the surface and returns to its original position in time t1. Next, the ball is released and it falls through the same height before striking the surface of the liquid of density dl. So these are the four questions which are based on this information given in the main question. And the first states that if the density of the ball is less than the density of the liquid, we have to obtain the expression for the time t2 the ball takes to come back to the position from which it was released. Part B is the motion of the ball simple harmonic. And part C, if d is equal to dl, how does the speed of the ball depend upon its depth inside the liquid? Neglect all frictional and other dissipative forces. Assume that the depth of liquid is large. So this question is basically, you can say, into two parts. In the first part, it says that there is a solid surface. So let us suppose this is a solid surface, and ball is dropped from a certain height. Let's call this as point as A, and this ball strikes the solid surface, bounces elastically and returns to its original position in time t1. Okay, so it means, let us call this as point B. So the time t1 is the time taken to travel from A to B and back B to A. This is the first case. In the second case, it says that instead of this solid surface, there is a liquid. So let us consider this is the liquid, and it is dropped from the same height. So let us suppose the height is given as same as A, and it is going to strike this liquid surface, and let us call this liquid surface point as B prime. So obviously it is going to enter the liquid and travel some distance, and let us suppose it travels up to a distance of C, and because the density of this ball is less than density of the liquid, so you can say from B prime to C, the ball is going to decelerate, and this particular point, let us suppose at this particular moment, the velocity of the ball becomes 0, and after that it is going to be pushed upward because of the buoyant force, and it is going to retrace its path up till point A. So we have to find out the total time it takes from A to B prime, that is within the air, and B prime to C, that is inside the liquid, and then again from C to B prime inside the liquid, and B prime to A inside the air. Okay. So let us call this as initial condition. And this as final condition. So from this final condition, we can clearly see that the ball is going to interact with two different environments. You have mediums. One medium will be air, and another medium will be liquid. Whereas in the first condition, that is initial condition, it is only going to interact with only one medium, that is our air. But the interaction with the medium in the initial condition will be same, that is the interaction in the air medium in the final condition. Because everything is same, height is same, and the point from which is dropped is same, only difference is with the respect to the surface. Okay. So here you can say that we are going to make a analysis based on this entire discussion. So we can say this analyzing the motion of the ball with the density d as it interacts with two different mediums, as it interacts with two different mediums. Please keep in mind that the area medium in initial condition and final condition is same. So directly, we can say indirectly, we are only going to discuss two mediums, air, and when we discuss air medium, we are discussing initial condition medium as well as final condition medium with respect to air, and the liquid medium is only available for the final condition. Okay. Two medium. So let us call first as air phase, and this air phase, the ball bounces off a solid surface. Ball bounces off a solid surface. In this case, in the question itself, it is given that the ball falls under the gravity hits the solid surface and bounces elastically back elastically to the starting point, starting point is A, and it bounces by elastically from point B. So it means, and the total time that is given is, in the question, it is T1. So you can say total time, which basically means from A to B and from B back to A, total time of motion is equal to T1. That is given in the question itself. This is for air phase, and we can find out now interaction with the liquid, or we can say liquid phase. Liquid phase, so which is basically interaction with liquid surface. Interaction with liquid surface. So once again, for this liquid phase, the ball is dropped from the same height. Ball is dropped from same height, or we can say that is from A. Okay, from A point it is dropped, and but now instead of bouncing back, it you can say it falls into the liquid with density dl. but now falls into the liquid with density dl. Now upon entering the liquid, the ball experiences the buoyant force. The ball experiences the buoyant force in addition to its weight. And now buoyant force will be in upper direction and the weight will be in the downward direction. So it is going to experience buoyant force in downward direction in addition to its weight, which is in buoyant force in the upward direction, my mistake, and weight is in the downward direction. So it is given that as density of the ball is less than density of the liquid, the ball will decelerate. The ball will decelerate while going through the liquid. While going through the liquid, and ultimately it is going to come to rest, which we said will be the point C. So we say it is going to decelerate, and this point C, it will come momentarily to rest. Okay. Decelerate while going through the liquid, and reverses its motion from point C due to net upward buoyant force. Due to net upward buoyant force. And this total time is our suppose T2 in the question it's given. So we can say thus the time T2, this time T2 will be equal to from A to B prime, B prime to C, back from C to B prime, and B prime to A. So thus the time T2 will be equal to A to B prime, B prime to C, then C to B prime, and B prime to A. So this is the total time T2. So we have to find out this T2, what will be the T2. Now in order to calculate T2, we can clearly understand that the distance traveled from A to B will be same as that will be from A to B prime. So it means the time taken by the ball from A to B will be same that is from A to B prime. Okay. So let us calculate. We can calculate our this distance from A to B using the elastic collision theory. Okay. So let us first solve it for our air phase. So we can say it elastic collision with the surface. Now in case of elastic collision, the direction of the velocity is going to remain same, but only thing is that the magnitude is going to remain same, only thing is that the direction will be reversed. You can say in elastic collision, the ball bounces back with velocity having same magnitude we are only interested in magnitudes, so we will focus on this only term with having same magnitude. So from this we can draw a conclusion that time of fall means from A to B will be equal to time of rise, and time of rise means from B to A, and the total time is given as T1. Total time is given as T1. So from here we can say, because we are interested in either time of fall, because time of rise and time of fall will be same, so let us call it time of fall. So we can say our time of fall will be equal to T1 by 2, because total time is T1, so half of the time will be time of fall. Time of fall means from A to B will be T1 by T2, and let us call that as TF. So we found out the time taken by the ball from A to B. So indirectly we found time taken by the ball from A to B prime, because the distance is same. Now we come to the second part, when the ball strikes the liquid surface. When ball strikes the liquid surface. So let me redraw this figure here. So this is our point A, and this point is this is B prime, and we call this as point as C. So this time taken from A to B prime is our T1 by 2. This is our air, and this is our liquid. So we already know the time taken by the ball in the air is T1 by T2, and let's find out what will be the value of the velocity of the ball just before it is going to strike the liquid surface. So we say velocity of the ball just before hitting the liquid surface. And let us call that velocity as V. So we can use equation for kinematics. Use the equation of kinematics. V is equal to U plus AT, and as the ball is dropped, our u will be equal to 0, and time taken from A to B prime is our t1 by 2, t1 by 2, like this, and our acceleration will be free fall, that is g. So therefore we can write that our v will be equal to 0 plus half g t1, or we can say v is equal to half g t1. So this is the velocity just before striking this B prime. Next, we are going to find out now with respect to the liquid. Okay. And we know that inside the liquid, retardation is going to take place. So let us discuss that part. The retardation in the liquid So when the ball enters the liquid, it experiences two forces. One is a buoyant force in the upward direction. Another one is the weight of the ball in the downward direction. So we say when the ball enters the liquid, it experiences two forces. Buoyant force that will be in upward direction, let us call that FB, which will be equal to V multiplied by DL multiplied by G, where V is the volume of the ball, because it is completely submerged, so that the amount of water displaced will be equal to V. And next will be the weight of the ball, and this will be in a downward direction. Let us call that FW, which is equal to mg, and this can be written as V multiplied by density of ball multiplied by g. And here V is, in both the cases, V is the volume of the ball. V is the volume of ball. Let me write it capital V, otherwise it will be confused with the velocity. So therefore we can find out the net force on the ball. Net force on the ball, let us call that Fn, and equal to buoyant force minus weight. So we substitute the value, we get F net is equal to, we can take Vg as common, V into G, we have density of the liquid minus density of the ball. And this net force is going to be create an acceleration, which will be retardation in this case. So we can say, but Fn will be equal to mass multiplied by A, where A is our retardation. So we can substitute here, we get MA will be equal to Vg dl minus t, which can A is equal to V, G we have dl minus t divided by mass, and mass is nothing but volume into density. So our v cancel the v, we get our acceleration is equal to dl minus t divided by d and whole multiplied by g. This is our retardation. And now we find out what will be the time taken by the ball inside the liquid to reach point C. Okay, so this was our point B prime. Ball is retarding and this is the final point C, and we say this point is, let us call as D prime F. Okay. So we can say that time taken, and bear in mind this is the liquid. We say time taken by the ball to come to rest inside the liquid, let us call that T prime F. Come to rest means at point C. So once again we are going to use equation for kinematics. Equation of kinematics, V is equal to U plus AT. Now in this case the final velocity will be equal to 0. So our V will be equal to 0. Initial velocity is, we already found out, that is at what will be the velocity as B prime, and that U, we got this was our U was equal to G 1 by 2 G T1, and acceleration we just found out, and time T we said it will be equal to T prime F. So therefore we can say we substitute 0 is equal to half G T1, and this acceleration will be our deceleration, so this will be minus A, and the time is our T prime F. So therefore we can say that our T prime F will be equal to G T1 divided by 2A. So we found out the amount of the time that it is going to take inside the, you can say, liquid. Okay. Now we are going to sort out for what was asked for. Now we are going to substitute the respective values of A and get our this T prime F. So this is our G T1 divided by 2, and acceleration we found out is our dl minus t divided by d and multiplied by g. G and g cancel out, so therefore we can say our T prime F will be equal to this comes as, this goes up, d upon dl minus d and multiply by T1 divided by 2. So this is our time inside the liquid. Time inside the liquid from B prime to C. Okay. This is only from one side, the deceleration mode. Now we find out the time taken to go from C to B prime. So we say time to rise back to the liquid surface. time to rise back to the liquid surface. So basically means from C to B prime. So as in the question itself it's mentioned that we have to neglect everything. It says that we have to neglect the frictional and other dissipative forces. So from here we can draw a conclusion that we can say that since the retardation is constant, since the retardation is constant, therefore the time taken, thus the time taken to rise from C to B prime will be equal to time taken to come to rest. Time taken to come to rest. So which basically means from B prime to C. So and this rise time, if we denote as TR, so we can say TR prime will be equal to TF prime, and this is, it comes as d upon dl minus t multiplied by t1 divided by 2. Now finally we got all the times. We found out the time inside the air from A to B prime, and we found out time from B prime to C, and we also found out that the time taken from C to B prime will be same as the time from B prime to C, and obviously time taken from B prime to A. So this total time for an entire journey from A to B prime to C, C to B prime and back to the starting point A, which is given as T2. So we say total time T2 for entire journey. Total time T2 for entire journey. And here entire journey means A to B prime to C, C to B prime and back to A. Therefore, we can say our T2 will be equal to time taken from A to B prime, time taken from A to B prime plus time taken from C to B prime plus missed one thing here, I think. B, yeah, this is C and this is, one second, A to B prime C, yeah, this is, sorry, A. So time taken from A to B prime, C to B prime to C, my mistake, this was the confusion, and time taken from C to B prime plus time taken from B prime to A. So this time and this time is our air time. So we can write this will be equal to our, this will be our T1 by 2, and from B prime to C is our, we found out this will be was our d upon dl minus t multiplied by T1 by 2 plus this is our d upon dl minus t multiplied by d1 by 2 and plus from B prime to A is equal to T1 by 2. So every time is, you can say twice. This is also twice and this is also twice. So therefore our T2 is equal to 2 2 into T1 by 2 plus 2 into, and we have this as d upon dl minus t multiplied by T1 by 2. So 2 and 2 cancels out this here also, and from here we can take our T1 as common. So this becomes T1, and we have 1 plus d upon dl minus t. Now we take LCM. Now it is a simple calculation. This is dl minus t plus t dl minus t, and d and d cancels out, and I think I missed something. No, I think g cancel out, no issues. So we get this as T2 is equal to T1. We have dl minus d. So this is our time taken, total time taken. Okay. And so we found out, solved rather you can say part A. Now we are interested in part B, which states that is the motion of the ball simple harmonic. And for simple harmonic, there is one necessary and sufficient condition which states that if the acceleration is directly proportional to the displacement, then we can say that the motion is our SHM. Okay. But let us solve this as part B. So we found out that the acceleration in the air, or rather we can say we know that acceleration in air is given as g, and acceleration in liquid, which is basically retardation, acceleration in liquid we found out was equal to dl minus t upon d and multiplied by g. So in both the expression we can clearly see that there is no, you can say, relationship between acceleration and the displacement. So we can now draw here conclusion. We can say acceleration is independent of displacement. Is independent of displacement, or we can also say that acceleration is not proportional to displacement, not proportional to displacement, which is necessary and sufficient condition for SHM. So as this sufficient condition is not satisfied, so we can say that motion is not SHM. Motion is not SHM, but it will be periodic. But periodic. So this completes our part B also. And part C, it is given that if D is equal to DL, it means density of ball is equal to density of liquid. How does the speed of the ball depend upon the depth of the liquid? So let us solve part C. And part C, so we already found out that as the ball enters the liquid, there will be two forces acting on it, buoyant force which is given as V dl multiplied by G, weight which is equal to V d multiplied by G. And in the question it says that, part C rather, for D is equal to dl. So let's modify. Weight will be equal to V dl multiplied by G, because density of the ball is equal to density of liquid. Therefore, the net force, or from here we can say that our buoyant force is now equal to the weight of the body. Force because of the weight of the body. Therefore, net force will be equal to Fp minus Fw, which is equal to 0. And when the net force is equal to 0, this particular condition is called as a experiencing neutral buoyancy. Experiencing neutral buoyancy. As the net force is equal to 0, so we can say from here that Fn prime will be equal to mass into acceleration, which is equal to 0. So we state that our acceleration will be equal to 0. And we can use equation for kinematics. We can say that using equation from kinematics, equation of kinematics, V is equal to U plus AT, acceleration is equal to 0. So therefore we get our V is equal to U, or we can say final velocity is equal to initial velocity. And this we are talking with respect to the liquid. And initial velocity inside the liquid is our G by T1 by 2. You can say, but initial velocity inside the liquid is equal to G T1 by 2. So therefore, V will be also equal to T1 by 2. So as initial velocity is equal to final velocity, so we can draw one important conclusion, that the ball moves inside the liquid with constant velocity. We can say the ball moves inside liquid with constant velocity. And that was our part C, which says that how does the speed of the ball depends on its depth inside the liquid. The speed of the ball is independent of the depth inside the liquid because it travels with constant velocity. So therefore we can say that speed of the ball is independent of depth of the liquid. Depth of liquid. Please keep in mind here depth of liquid is indirectly representing the acceleration, which in this case was retardation. But in the calculation part we found out that value of A will be equal to 0. So therefore the speed of ball is independent of the depth of the liquid. So this completes all the parts A, B and C for this particular question. Thank you.